Good morning, everybody. Welcome to this session one and the keynote number 3. Great to see so many of you here bright and early after last night's dinner and drinks. It's excellent turnout for first thing. So our first speaker today is Dr. Rick Henry. Rick Henry is a senior lecturer at the University of Auckland with expertise in seismic design of concrete structures. He leads the structural discipline theme in Quake Core and is a council member of the Concrete New Zealand Learned Society. He's previously served on the technical committee of the New Zealand Concrete Structure Standard NZS 3101, and as you're aware, he's also involved with a lot of concrete low-rise panel research. I'd just like to invite Rick to the stage now to give his keynote presentation. The next big thing or the next big failure.
Excellent. Thanks very much, Carl. I worked really hard on coming up with a really catchy title for this and maybe succeeded too much. And I think, as Paul said, I got the hang of a slot in the morning, and I'm glad that you're here, Paul, to enjoy it. So I'm going to be talking about innovation, and I guess to me innovation is one of these classic buzzwords that we like to throw around, very heavily utilised in marketing material, and no doubt in various conferences it's been in the byline of things, luckily not this year. But along with other things, resilient, sustainable and things, I think we often use them without really thinking about what we mean. And in a way, it's a way to promote things which doesn't necessarily have much to sort of confirm what that is. So I guess starting with the definition, I looked this up and came up into the dictionary and found that innovation is a new method, idea or product. Makes sense, right? But thinking about that more, it doesn't really imply that the new method, idea or product needs to be better than previous methods, idea or product, right? So it just needs to be new. And it doesn't really imply anything about what you need to do to prove that it's a good idea as well, or that there needs to be any evidence required. So I've sort of proposed this alternative that perhaps we should think about it as that innovation is really just an untested new method, idea or product, and that we should be aware of that when we're adopting these things and not just sort of assuming that new is better, but that we look and make sure that we're conscious of that evidence and verifying it. So I want to start off with this example because it got me thinking about this quite a while ago. Obviously an iconic bridge most will recognise in Auckland. Some might describe as rather ugly looking or not so iconic. Somewhat controversial in many cases, and recent news has sort of highlighted some more discussion around the bridge replacement and the cycling sort of options for the bridge as well. But it's sort of commonly used as a bit of an example in New Zealand of perhaps failure of our long-term thinking, where we built it in 1959, almost immediately didn't have sufficient capacity, and so 10 years later we had these clip-on lanes added to the outside that doubled the capacity. And it's those clip-on lanes that I wanted to focus on, because there was a really interesting presentation by Will Pank back in 2012 where he came to the Auckland Structure Group and presented on some of the strengthening they'd done in those box girder clip-on lanes. And he was explaining how really at the time they were an extremely innovative solution to this problem. And box girder bridges had been built overseas, but this was significantly longer span than some of those, 240 metre span, very slender, somewhat of an elegant profile. It sort of drops to about 3.5 metres at mid-span. And that's resulted in a bridge that obviously has worked from sort of point of view of the structure, but is very flexible. And that flexibility obviously has contributed to some of the difficulty in sort of maintaining and repairing it, and fatigue issues, which have resulted in quite a number of repairs throughout its life, which is only just sort of reaching 50 years. And he made this comment right at the end of the presentation, which I think summed it up quite nicely, in that, I'll quote him here, was the Freeman Fox approach to lean and mean design for infrastructure assets sustainable? I suspect not. The bridge isn't going to see its 100-year design life. So he was sort of making that observation that by pushing the boundaries of design right to the limit, maybe we're going too far, and it's those unknown factors that we haven't accounted for that are going to sort of tip us beyond what we actually wanted to achieve. And I guess the other observation here is that if we look at Christchurch, we know that prior to the earthquakes, Christchurch was predominantly built with reinforced concrete buildings, multi-storey structures, and they were quite heavily damaged during the earthquakes to the point where repair was difficult, and many of them subsequently demolished. And in rebuilding the city, obviously people were conscious of not repeating sort of those mistakes and obviously wanted to adopt different systems. And so we see in Christchurch that there is a whole array of new sort of systems being adopted, many with a lot more architectural sort of appeal perhaps than what was there before, but big range in structural systems, right? And a lot of them are sort of promoted as low damage. I'm sure innovation was used in many of the sort of material for these systems. And the question of that really is that by moving to new systems that we've adopted here, have we succeeded? And I think many people would say that, sure, some of them are probably going to perform really well, but no doubt some of them won't. And we might find that some of those low damage or innovative solutions don't succeed. And so I guess that's what I'm sort of reflecting on here. So if we think about innovation, there's two sort of categories that come up commonly. One is radical innovation, where really going for a significant departure in past practice or trying to change things or flip them upside down. And you sort of think of those as the high risk, high reward, right? We can totally change the way we do something. We might come up with a really good solution. And I think in our field, perhaps one of the best examples of that would be base isolation, right? Where it was quite a radical idea of sort of changing the way we might design buildings to resist the ground motion, and by and large, extremely successful. We know that the early designs weren't perfect, and Ken was talking about yesterday some of the moat pounding. And so we've incrementally sort of improved the way we do it, but the general concept was sound and very successful. The other way that innovation sort of comes through is through this incremental process, where we're slowly improving and refining designs or methods and sort of changing them as we go. And I think that's quite common in our industry. It was mentioned yesterday around the sort of bespoke nature of our design. We don't do sort of a lot of repetition. We're often doing things as one-off, and so we're incrementally sort of changing or adapting things we've done in the past. But it's also extremely common in a seismic design context where a lot of our lessons come from observations in past earthquakes, where we look at what didn't work, we reflect on that, we improve it, and we adopt that in our designs. And so that's sort of really important in the process, and I guess you would typically think this incremental change might be lower risk, but we should sort of be conscious of the fact that if you incrementally change things a large number of times, the end product can be quite a lot different than perhaps the original solution. And so I think it's sort of a frog in hot water scenario where you don't realise things are changing as much until you reflect back on perhaps where we came from. And so I think in design standards, this is really important because we know that incremental improvements need to be implemented in our design standard and that they need to reflect best practice knowledge at the time. And I guess this is a frustrating point for many of us at this stage because we don't feel like that's happening. And we supposedly have a 10-year cycle of revision for these standards, and I think most of them are not achieving that. So I think there's a lot to be sort of thought in that process of how we improve that. Perhaps some role that the technical societies need to play in terms of developing this idea of standing committees, trying to incrementally improve and develop draft material that we can make sure is out there and circulated. So I want to go and look at a few examples, and I guess it's somewhat titled as failed innovation. And really, I guess it's easy to look back and be critical of things in the past with hindsight, and so I'm not intending to do that in that way, but I think Carl summed it up really nicely, that sort of looking back before we look forward, and I think we're well aware of those sort of the need to observe and learn from lessons of the past so that we don't repeat them. And so I want to show a few examples of that, and it's really going to focus on precast concrete. You might read into that it's perhaps worse than other systems, but it's really partly just because that's something I know and do quite a lot of work in myself, so I think it's sort of good examples to use. So let's have a look at precast concrete. Well, it's a very commonly used system in New Zealand. We adopted a lot of precast concrete. sort of starting in the 60s and 70s and through the 80s building period, we really went all in on precast as an option for a lot of our concrete structures. And I've looked back at some of the sort of papers around this, and I pulled out a couple of quotes which I think are quite good to reflect on in terms of what people were thinking at the time, and it comes back to this idea of innovation. So a couple of quotes from Professor Bob Park when he was summarising what was happening. The increased use of precast concrete in the 1980s required considerable innovation because of New Zealand's location in an active seismic zone. So we were adopting things that had sort of been done overseas in cases, but we were dealing with them in the context of our seismic hazard and having to do things that hadn't been done before because of that, and a lot of things were sort of developed in New Zealand to account for that. He then goes on, well, with the increased innovative use of precast concrete came the increasing concern that some of these design solutions needed to be more researched. And so they were aware of that perhaps some of the implementation had preceded research, and it really was through the 1990s where there was quite significant research into precast systems to sort of confirm and address some of those things. And the last one here comes from the Precast Handbook. Significant developments in the use of precast concrete have been made in spite of the fact that some aspects have not been formally codified. It reflects the ongoing innovation by New Zealand practitioners that will no doubt continue. So again, sort of aware of this idea that we're often going beyond what our design standards have been written for and sort of pushing that boundary of what we think of in terms of innovation. So if we look at precast concrete, just to avoid being too critical, you always need to look at the positives. And by and large, many of these precast systems that were developed did work well. They worked the way they were intended to work. And we see in many buildings in Christchurch in particular where they had quite commonly used precast frame systems with various different connections. A lot of them actually did form beam hinging in the way that was expected, and by and large that was good performance from a structural point of view in terms of life safety. Not so much from the repairability, but that's sort of something we're moving into. And so a lot of things that did work. The things that didn't work. You can't go past Holocore. It's really the most obvious example in this case. And Holocore sort of introduced really in the 70s, but probably through the 80s, where it really started to be widely adopted and very quickly became the predominant flooring system that we use. And I've no doubt that when this was being marketed, people thought of it as an innovative solution. And it was very efficient section, resisting long span loads, cheap to produce, and speed of construction was a significant advantage. And so we adopted this in many of our buildings and sort of later started to address some of the concerns around seismic performance. And so it wasn't until perhaps 30 years later where we properly understood from research and from earthquake observations perhaps some of the things that we had missed. And in particular, this is around the idea that due to the interaction of the flooring system in the entire building and some of the deformation compatibility that needs to be addressed, these units are extremely brittle and prone to failure modes that cause concern for life safety and had to be addressed in the detailing, but also generally high damage. And even a well-detailed holocore will sort of be subjected to quite a bit of damage in earthquakes. I'll leave that there because Nick and Frank are going to talk a bit later about some of the Richford and sort of assessment aspects of these holocore units. But I think it's sort of quite clear when you look at this timeline that was put together of perhaps how it got to that point where we were adopting things early, and it sort of shows here where there was a long period where we were implementing it prior to perhaps the early work that looked at the seating, and then into the 2000s when perhaps those deformation compatibility issues really came to light. And so it was a long period of time where we had been building it with what we now know to be deficient details. And even more recently, perhaps following Kaikoura, has been the sort of realisation that the assessment and retrofit needed to be significantly worked on to get solutions there as well. So another one from Precast Concrete, which has been shown before, is this idea of the shear yielding link in beams. And so there's many ways that you can connect precast concrete frames. And in some short span sort of configurations with high shear demands, the idea here was that rather than trying to force beam hinging at the ends of the beams like we typically have, stiffen them up with some additional reinforcement and have a diagonal yielding element through the middle, similar to how we do in diagonally reinforced coupling beams. And so the concept was proposed and in theory works on paper, and some tests were done to look at whether this worked and found that it didn't really perform the way it was expected to. And so during the test, rather than yielding those diagonal bars all the way through the middle, it tended to concentrate at the ends of the bar or where the sort of relocated hinge portion had come to. And there's some nice sort of diagrams that were done by Richard Fennick, I think, on some strut and tie analysis that sort of highlighted the issue of in 2 dimensions it looked quite straightforward, but when you consider the 3rd dimension of things, then you started to realise it was a bit more complicated in terms of the load path and that there was a bit of an offset which caused that yielding to occur in places we didn't expect. And so it's a good example where testing was used to highlight that, but it was installed in a couple of buildings prior to that test, and so we do still have that legacy of sort of implementation just preceding the sort of validation of the concept. And the last one here is something Carl mentioned already, but we've done quite a bit of work on these panel base connections, and I think, I'm not quite sure you'd describe this as innovative, but simple and quite commonly used for a number of years. And I think another case where the detail was used perhaps without adequate consideration for whether it had been really proven to be a good, robust detail. And we're looking at sort of inserts used at the base of the panel to create this dowel sort of connection from the panel into the foundation. And we now know that those inserts are too shallow to develop the complete load path, and also that perhaps design procedures assumed that they developed pull-out sort of capacity in a breakout failure mode, when in reality you look at the interaction of the flexural demands of the panel and the cracking, and you don't achieve that. So the design method needs to sort of be adjusted to account for the real behaviour. So some initial sort of thoughts from that is that really, this idea of radical innovation being a big departure from existing knowledge really needs to be pretty well understood and tested prior to understanding it and thinking about whether it's a good solution. But also on a more simple level, lots of our design assumptions and simplifications might seem straightforward, but we actually need to really go through some detailed analysis and testing sometimes to understand whether those are correct. And I guess the last point is that we need to really define this point at which incremental change starts to become an issue where perhaps the increments cause the end product to be a different outcome from what we originally had. And I've shown this before at a conference, but I think this is a really interesting comparison where there's a documentary on Netflix called The Bleeding Edge, which looks at medical devices. And it's sort of typical dramatic style of documentary, perhaps lacking a bit of fact-checking in places, but I think the general idea sort of still seems to be relevant in that they were looking at medical devices and thinking, well, the same idea, we've had failures of products that were approved, how did we get to that point and what can we do to avoid it? And it sort of looked through and found that they developed this quite rigorous approvals process in the 1970s where all of these new devices would have to be clinically tested and go through quite a stringent sort of process before they were approved for use. And that was sort of quite successful in that sort of process. The companies pushed back and said, well, there's a long time frame to develop and clinically test these products, and that's really a bit of a roadblock to innovation. If we're going to develop really clever solutions quickly, then we need to have another way of doing it. So they lobbied and they came up with this exemption that was put into the regulations that said if it's a product that is substantially equivalent to a previous product that's been approved, it's okay, you don't need to test it, you can just go through this exemption of being substantially equivalent. And in the documentary they sort of went back and looked at the approvals of these products and found that 98% of products were substantially equivalent to something else. Effectively 2% of these medical devices were being tested. And there was plenty of clear evidence to suggest that a lot of the failures were a direct result of this sort of substantially equivalent clause, particularly because it had no definition of what was substantially equivalent. And there were plenty of things that used that where there was clearly a significant change that really should have been tested. But also, it could be substantially equivalent to a product that was defective and you could still use it. And so it was just a little bit ridiculous in terms of how some of the regulation was being adopted. But it got me thinking of that, well, in structural engineering, what is substantially equivalent to us? And I think we do this a lot. And it's good to reflect on what we define as substantially equivalent, or when a departure is so much that we no longer have confidence that we know what we're doing. So some examples again. Shear. In reinforced concrete, we know that early shear provisions for strength of concrete were developed based on very small scale tests. And so the tests that were done in the 1950s and 60s, typically 150 to 200 mil deep beams, and used to develop empirical strength predictions for shear. As we developed increasing testing capability, we went to deeper and deeper beam tests, and more recently a test that Professor Collins and his team have done up in Toronto of this deep slice of a foundation pad, which is probably the deepest beam that's ever been tested. And they found that it didn't actually scale in the same way, and there's a massive size effect where as the beam depth goes up, the equivalent concrete shear strength goes down. And they only found that by doing deeper and deeper beam tests that were more realistic of what people were actually building. And that idea of extrapolating beyond perhaps a data set that we use for empirical equations is really quite dangerous in that sense. Another example of concrete structures in terms of these lightly reinforced walls we've seen, where our design provisions are on the basis that we get plastic hinging at the base of the wall. And previous tests have shown that we get good plastic hinging. We can develop the sort of detailing requirements for that. But when we implement them in practice, we don't necessarily implement it in the same way. And so in some cases, particularly in areas where they didn't need heavily reinforced walls and precast walls had quite light reinforcing, we had these situations where building in Christchurch that had a single crack and fractured all of the bars. So a building which was intended to have ductility, but because we'd gone and pushed the limit a bit too far in terms of the reinforcing content, didn't achieve the intended outcome. Buckling restraint braces. This is a relatively hot topic and very successfully marketed in many senses, been adopted in a wide range of buildings, and a number of people, including steel experts, which I'm definitely not, have expressed concerns in how that's been done. And one of the examples of that is that the gusset plate detailing perhaps was adopted in some cases from sort of design provisions used for concentrically braced frames, where buckling actually is part of the design philosophy. And when you use a flexible gusset plate with a buckling restraint brace where you need to keep it axial tension compression, you might end up with this. And so it's a good example where we're sort of adapting existing knowledge and ideas to a new system and perhaps missing out a few steps along the way. Another one which we've been looking at more recently is these buildings that combine concrete walls with steel frames, and it's one of the most popular sort of systems coming through in Christchurch at the moment. And again, these steel beams that frame into the walls often use sort of web plate detailing, which is common in steel construction, and there's a very well-developed design procedure with good sort of indication of strength hierarchy and sort of how you follow things through. But when you replace that column with a concrete wall, I don't think there's any design procedure that shows you the equivalent of how you do that. And so we've looked at sort of drawings and found that people are doing a lot of different things. And there's no doubt going to be a range in performance from some of those designs based on people's assumptions and sort of how they implement those details. So something that we need to sort of stay ahead of in terms of ensuring that we update things. Dissipating devices. There's been a lot sort of talked about this in the past where we have an increasing use of dissipating devices and structures, and a lot of these go through quite rigorous testing prior to being implemented in buildings, and I've just shown a couple of examples that have been presented previously. And in some cases, they've shown failures of the device sort of where we wouldn't have necessarily predicted in design. And I think it comes down to sometimes that the actual details of it are really important, and it's difficult to sort of imply that previously tested device is substantially equivalent. But also there's been cases where small-scale things tested in the lab, perhaps in a research sense, and then scaled into a real structure where they're significantly bigger, they don't achieve the same performance. And so there's also the scaling or size effect that can occur in some of these situations. And another one on model validation. I think this was quite nicely described in John and Tony's presentation yesterday around some of the modelling assumptions and things. But I've made a couple of points here where I think in the same thing as was talked about, the models sort of tell us what we want, in that by the formulation of the model we are actually constraining what the output's going to be, and so it's sort of biased to our assumptions of the inputs. And if we don't get those right, then we can't sort of expect the output to be something different. But also when it comes to validation, this idea of substantially equivalent is really important too, and that I've used this example here, which comes from sort of performance-based design of tall buildings in the US, where they're developing really sophisticated nonlinear models to do time history analysis of these buildings as part of the design verification. And in many cases, the sort of models used in there are validated against very small tests. So they might take a small rectangular concrete wall to verify that their fibre element in the model gives us good response. But as you know, is that little concrete wall even remotely similar to that complex core wall in the building? Not really. So do we really have confidence that we can take that model and apply it to the core wall and actually catch everything that's important in terms of its behaviour? So that's some examples, and I guess to sort of think through perhaps looking at those cases and where some of the causes, I've come up with a list of things that I think are sort of important in terms of those observations. So first would be perhaps many cases where we have inadequate consideration of the loading case. And so we might be designing something thinking it's for gravity, but the deformations induced due to seismic demand cause additional actions that we haven't considered. And so adequate consideration for all of the load cases is really important to think about how we use things. We might have a design flaw in the idea, and we can come up with ideas on paper and in models and things, and they won't always be correct. Sometimes we need to test them, and a physical test is a really great way of verifying whether that works. Those of us that do experimental testing know that even when you have some of the most predictable systems, you always find something unknown when you do a test. There's always something that you didn't see coming, and in some cases those are really significant. Also in terms of testing, sometimes a heavy reliance on testing that doesn't really replicate the conditions of the element. And that might be related to this idea of scale, testing something small when the actual reality is something big. Geometry, that we commonly test things assuming regular structures, whereas structures in reality are highly irregular. And we often have to simplify the boundary conditions to be able to achieve things in the lab. And that's a limitation of what we can do, but we have to really test the assumptions that we're using there and make sure that we're not missing things. And that links to the last one, which is that there's really a growing understanding that by testing components and expecting an entire system to perform well is not really going to get us all the way there. And that's increasingly important when we think about this idea of low damage structures, where it's not just the performance of the component, it's the performance of the system which is going to get us the outcome that we want. Unfortunately, it means much more difficult processes in terms of what we do in terms of experimental testing, but capabilities of that are obviously increasing too. So coming back to the two types of incremental innovation, starting with incremental innovation. If it's a small extension of a known system or a known idea, then we need to think about the evidence required, but it's often to deal with things that are perhaps known unknowns. So we know that we're extrapolating something, we know that we're going a bit beyond an existing thing. Let's test out those assumptions and check whether they're correct. So that would be sort of, does the size effect exist in concrete beams? Some things to think about. Well, obviously that point of extrapolating, we often get into that problem of extrapolating because we don't have data available or we don't have experience to go beyond that. And then also back to that point that it could be substantially equivalent to a system that doesn't work. So just because something is currently used doesn't mean it works or that it's been proven and has evidence. We commonly get into this pattern of using things because they've been done for many, many years. It doesn't mean there's any evidence. And as came up yesterday, any new idea or system, don't lose track of the basics. Everything should have a load path, everything should be well understood, and sometimes simple back of the envelope calculations are going to fix something that you obviously missed. And then perhaps the last point is that maybe we're just going to have to test some things all the time. So dissipating devices come up in that maybe proof testing and BRBs are the same. Maybe you're just always going to need that because there isn't the ability to come up with a substantially equivalent sort of procedure to be confident that they're always going to work every time. When it comes to radical innovation, well, I think this is where we need to be more careful. And if it's a substantial difference from an existing system, then we need to be very cautious and not just jumping in before sort of dealing with the facts. And I've sort of summed that up in that you're dealing with the unknown knowns and the unknown unknowns. And so there's these sort of various ways of looking at it, but it's the things that we don't know we're going to find until we try and look or until we get earthquakes and we find them. And it's really more difficult, obviously. But one way of doing that is to say that the research that supports the implementation of these radical systems needs to be done in an incremental fashion. So we build it up from something we know to something that's more complex that represents that reality. And I don't think anyone should be doing anything radical without some evidence. Evidence can come in different forms, but I think we need to be very cautious about that. So one example in my field of sort of concrete structures, we've gone through this process, and I think it's a good example of how this can happen, where for concrete structures we have post-tension walls and we have slotted beams that have been developed as a concept. We can draw them and come up with mechanics of how they work on paper. We can go and do component tests, and there's been a huge array of component tests on these systems done in the lab, and that helps us build up understanding and confidence in how the component works. We then go and extrapolate that a bit further to sub-assemblies where we introduce interaction with surrounding systems, in this case sort of with the floors and things, starting to subject them to different types of loading, bidirectional loading and things. And then once we're confident in that, if we're able to, or if it's necessary, we might go and do a system test where we start to include all of those things. And in this case, we were able to do that on the shake table facility in Tongji. And a good example of that through here is with these slotted beams where they knew that when this was developed, there needed to be an ability to take torsion from that beam through that connection. And so there was a procedure to address that, and in the component test, they sort of made sure that there were torsional demands to test out that theory. But when they came to the sub-assembly, they found that there were additional torsional actions generated from the floors that hadn't been included. And so there are things that, looking back in hindsight are obvious, but we now know we need to include. The design procedure was updated. We used that in the system test with the updated procedure, and it worked perfectly. So we can incrementally improve things if we have time and the ability to find those unknowns. So coming back to the question of these sort of new buildings and things, I think reflect on all of these new structures we're building and perhaps these crazy structures that we might be building. Are we on the right track? Are we confident that we can look back at each of those buildings and know that they will perform the way we expect? And I guess the other way to think about that is, have we adopted the next holocaust? That's the way I like to think, that are we preventing ourselves from following that same pattern and implementing something where we reflect 30 years later, I wish we didn't do that. And I think in some cases we should really think hard about that. And something that I don't know if people agree with, but sometimes I think it's better the devil you know. There are plenty of systems that are not perfect, but that we know a lot about. And I think that sometimes we've got a lot more confidence implementing them than a new idea that we might think is a great idea, but we don't know anything about. So that's one thing to think of. So I thought I'd finish with things that I think I'm a little concerned about. And I think these are things that might need some additional thought, or that we might be falling into that trap. So I'm just going to put these up as my ideas. We'll see if people agree with me or not. My first one would be precast walls. I think we use precast concrete walls in the majority of our buildings still, from low-rise to multi-storey buildings. We love it in Auckland particularly. And if you look at the evidence, we know a lot about reinforced concrete walls designed for ductility with good detailing. We even know a lot about post-tension walls designed for ductility with those low-damage solutions. Comparatively, we don't know much about these. A lot of the details we still use in these precast walls, particularly the singly reinforced details, they don't have the evidence. And we know from testing that has been done that many of them don't perform as good as we want. So I think there's work to be done thinking about those buildings. I've mentioned it already, but BRBs. I think there's still a lot of concerns around BRBs, how they're implemented, and whether that's correct. Heard concerns about potential soft story. I'm not sure if that's something that's been properly addressed. There's issues around bidirectional demands and whether we've actually understood and tested that. It would be great to see a large-scale test of a BRB building because I don't think that's currently occurred, and I think we might find things. As I mentioned earlier, looking at buildings now, we don't design concrete, timber, or steel buildings. We design buildings with a bit of everything. And it's more common that we're seeing mixed systems. The idea that we've got a dual system, the connections between these, which when we compartmentalise our material standards into concrete, steel, timber, sometimes get missed. And they're highly irregular in many cases. So we're going well beyond that concept of regularity when we come to these types of building. And I think we've got a lot to learn about some of those structures too. Multi-storey timber. I think the mass timber construction's been extremely successful in coming through, and there's often news articles about these super tall timber buildings. Personally, it scares me. And I think the concern is relating back to the precast scenario. Are we going to adopt something that might sort of have been successful from a non-seismic sort of perspective, and that when we look at the seismic considerations, it doesn't stack up? So I think enough consideration needs to be given to some of those things before we go all in. And the last, this has been mentioned before, but these sort of increasing use of gadgety, high technology devices where we think that to be good, it has to be high tech. And the use of these sometimes makes our structures more complicated and more unlikely to sort of be well understood or known, and I think that comes to John's point on precision and accuracy too. So I think sometimes we're going too far in that, and again, simple things we understand are really important, and we could do a lot more better things with that than jumping to the most high-tech solution. So with that, that's all I have to say. Thank you.
Thank you, Rick. Excellent presentation and also excellent timing. So we have probably enough time for 4 or 5 questions because he's finished a couple of minutes early. Have we got anyone out there?
That worked. So thanks, Rick. That was really good. And it's really encouraging to see someone questioning the use of the word innovation, which is all pervading. I was kind of intrigued, and I'll ask you to comment. You put up the root causes, but I think the causes you put up there were largely technical, whereas I feel there's a sort of a human factor cause. So picking up on some of Gordon's comments yesterday, seems to me as a profession we're all wanting to get the jump on everyone and be the person who puts out the next big thing and can use that for our marketing and the works. Perhaps we're lacking in the collegiality which requires us to actually sit and work together to make sure things are right. Could you comment on perhaps the human factors of this?
Yeah, completely agree. I think I've definitely taken a very technical lens to looking at those. So I think in terms of root causes, that the human factor and the way that we work together would be massive. I think, my opinion is that we're already making huge strides in terms of sort of the collaborative nature and what we're doing. At least from my point of view in the research sense, I think we're in a much better place than we've ever been. And I think that some of that will help us to resolve those challenges.
Do we have any other questions?
I think the increased use of peer reviews and peer reviews that are done properly and collaboratively is really helping with this collegial approach and sharing ideas, and certainly jobs that are done and started at the right time. I think is working well to share ideas and sort of break down some of those cards close to the chest sort of barriers of the past. I don't know if that's working well, throughout the country, but I think it has in Christchurch.
Sure. Is it just on? Yep. Okay. Actually, that's not a bad segue. Thanks, Craig. In the US, with the performance-based design procedures that started to come in for tall buildings sort of 15 years ago, 20 years ago, one of the things that cropped up there was that the peer review team comprised of a practicing structural engineer, practicing geotech engineer, and an academic structural engineer. Now, I'm not trying to lump more work on everybody, but do you think there is potentially a need where a building sort of hits a trigger of innovation or something dramatically different, that needs to be potentially part of the peer review team and actually bring in someone who has not necessarily the need to do the research on it, but has the breadth of knowledge of what's out there to go, you probably need to be reading this information. Is that something that would be too onerous for New Zealand to look at adopting and finding that?
Yeah, I think potentially some balance between at a project level versus at a higher sort of consideration of systems and things that could be adopted, but it's certainly an approach I think has some merits, and getting people from different sort of views and opinions. I think there's often evidence that exists on things for or against that might not be well understood in the public domain, and things that could be brought into that process from different people.
I'm just wondering about we talked a lot about the designers, but what about the manufacturers who are coming up with these kind of their gadgets, or how do we involve them in the conversation, and perhaps how could we do that in a better way than we've involved the manufacturers of hollow core in the past?
Yeah, I think my opinion is there needs to be significantly more openness and sharing technical data. And I think that the onus is on those companies developing product to have undergone that process and to be able to prove that to people. And, I can easily say this because I don't have to put myself in that position as an engineer having to sign things off, but I wouldn't be comfortable using a product that I didn't see the data or understand what was done. I'm not sure we should be sort of just taking people's word for it, or historical use as a basis of evidence. So I think understanding the evidence and the data and being more open about sharing that in a way that we can actually benefit is crucial, I think.
Following on from both the last questions, something's been on my mind for some time. If hollow core or something less obvious was being introduced today, if and what checks and balances would there be to ensure it was put through its paces, and should we be having something? And I'm talking about a system at a nationwide level rather than at a project level.
I guess I can share my opinion, which is I'm not sure we would stop that. I think there's still gaps in our process and thinking that could allow sort of ideas like that to still be adopted in that way. And I think that's some of the ideas I'm thinking of are still occurring, I think, in that sense. They might not be as bad as hollow core. Maybe they're different in a way, but I think we're still potentially falling into that trap. And I think there isn't any, really rigorous expectation of what needs to be thought through in terms of these new systems. We still have a tendency to jump onto a new solution to address the old. And I think the example with flooring is that, we've really understood precast floors, and we know they're not great, and some of them shouldn't be used, but we're also adopting an increasing use of other types of floor. And I think there's a general expectation that they're more robust and likely to perform better, but there's also not the evidence to prove that too. And I think there's no doubt we're going to find some things in that, particularly perhaps due to damage that's unexpected, that surprises us too. So I think,
Last question, Ken Elwood.
Yeah, and I'll make it short. More of a comment. This seems like a great challenge for CSOC. And I challenge the management committee to maybe consider how CSOC's role in trying to manage these future innovations, and probably trying to serve the role that Jeff was suggesting we need to have.
I'll come and collect that from you later. Okay, really good discussion, and I'm sure we could start talking for another half hour on this actually once we get going with the real questions. But if you could all put your hands together, thank Rick Henry, that'll be great.